All right, we are back at AP Review. This is 2009 BC Free Response 6. The Maclaurin series for e to the x is this, which we should all have memorized anyway, just to be clear. Most APs aren't going to give you the e to the x Maclaurin series. The continuous function f is defined as f of x equals e to the quantity x minus 1 squared minus a 1 all over an x minus 1 quantity squared. My bad, that's squared. Okay, cool. For x values that are not 1, and then f of 1 is equal to 1. The function f has derivatives at all orders, derivatives of all orders at x equals 1. Cool. Part A, write the first 4 non-zero terms and the general term for the Taylor series of e to the quantity x minus 1 squared, about x equals 1. Okay, so essentially all they're asking us to do now is we have the e to the x, right? They're saying if we wanted to write e to the x, the quantity x minus 1 squared, we would just replace every x we see with an x minus 1 quantity squared, right? So, for part A, right, e to the x minus 1 quantity squared is going to equal, the first term is just a 1, there's nowhere to plug anything in, so it's still just a 1. The second term is an x, so instead of an x, I'm going to plug in an x minus 1 quantity squared. The third term is an x squared over 2, so I'm going to plug in an x minus 1 squared and get x minus 1 squared squared, which is x minus 1 to the 4th over 2. The next term is an x cubed over 6, so that's going to be an x minus 1 squared cubed over 6, which is going to be an x minus 1 to the 6th over 6, right? And then my last term, right, we're just going to do the same thing, but we're going to plug into this nth term. So it's going to end up being an x minus 1 to the 2n, because it would be x minus 1 squared to the n over an n factorial plus dot dot dot. So always double check that you did exactly what you were asked. We were asked to write the first 4 non-zero terms, which we did, and also the nth term, which we did. Cool. Part B, use the Taylor series found in Part A to write the first 4 non-zero terms and the general term for the series about f. So notice, oh, this is kind of fun actually. So notice what's happening in B, right? I'm taking this series, I'm subtracting a 1 from it, which is magically going to take care of this stupid 1 problem, right? So what's going to happen is my f of x is going to be this series, right? So 1 plus the x minus 1 quantity squared plus the x minus 1 to the 4th over 2 plus the x minus 1 to the 6th over 6 plus dot 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 the x minus 1 to the 2n over n factorial plus dot 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 dot. But then, and here's the fun part, again, I totally do find it actually fun, I'm supposed to subtract 1, right? Which is relevant, because I'm going to show you why in a sec, okay, divided by this x minus 1 quantity squared. Okay, so the reason that this is totally awesomely legit relevant is that this minus 1, if you put things in a slightly different order, gets put with this plus 1. They're the only constant terms, and they totally cancel. So what ends up happening is that f of x is x minus 1 squared plus x minus 1 to the 4th plus x minus 1 to the 6th. Sorry, I am going to put the stuff on the bottom. I'm just trying to get all my powers done. Okay, x minus 1 squared is not over anybody. X minus 1 to the 4th is over 2. X minus 1 to the 6th is over 6 plus dot 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 dot. X minus 1 to the 2n, right, over this n factorial dot 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 all over an x minus 1 quantity squared. Well, what's going to happen is that we can cancel that x minus 1 squared out of all of these guys. So my f of x is going to be, well, x minus 1 squared over x minus 1 squared is going to be a 1, right? This is going to end up losing 2, right, because that's what we're doing, is subtracting 2 of the x minus 1s. So this is going to end up being an x minus 1 quantity squared over 2, right? This is going to lose 2 of them, so it's going to end up being an x minus 1 quantity to the 4th over 6, right? Now, they asked for the first 4 non-zero terms, which is a tricky thing of them because there's one more that I'm missing that I'm going to have to write. So I don't know this next term, so I'm going to actually have to figure out what it would have been, right? So I know that this was when n was 1, 2, 3. So I need to figure out what the n to the n with a 4 term would have been. Well, that would have been an x minus 1 to the 8th over a 4 factorial, right? This right here would have been an x minus 1 to the 8th over a 4 factorial. So now when I lower that power by 2, it's going to be an x minus 1 to the 6th over, and you can make it a 4 factorial. You can write it as a 24. It's up to you. I would say anything past probably 4 factorial, you're okay to leave as a factorial. And then when I get to the nth term, I'm not dividing this by 2. What's happening is I'm subtracting the exponent. So I'm going to get, this is an x minus 1 to the 2n minus 2 over an n factorial, right? So that's what I want. So again, sometimes something cool happens, and that's totally why they threw this -1 in there into the F formula, was so that it would magically cancel, and you'd be able to clean it up. So my first four terms are this 1, the x minus 1 quantity squared over 2, the x minus 1 to the 4th over 6, the x minus 1 to the 6th over 24, and then the x minus 1 to the 2n minus 2 over an n factorial. And the AP actually does have a slightly different answer here than I do, which is fine, because they called this, so mine would be starting at n as 1, right? If I started at n as 1, I'd have no x minus 1 term, and the n is 2 and n is 3. They did a slightly different formula. It's the same idea. They started at n as 0, and that was the difference for them. So again, mine starts at n as 1, theirs starts at n as 0. It's the same idea, slightly different nth term. All right, part C. Use the ratio test to find the interval of convergence for the Taylor series found in part B. Okay, so we need the Taylor series in part B, which was this guy. So I'm going to write him down just so we have him up at the top, because it's no fun when you don't have it, right? So let's recopy our answer for part B. Our answer for part B was that it was a 1 plus an x minus 1 squared. Oh, sorry, that's the one we just found. I'm slow. Hang on. Was a 1 plus an x minus 1 squared over 2 plus an x minus 1 to the 4th over 6 plus an x minus, I don't actually need all four of them, I just need the nth term. Okay, so the nth term is really all you need, x minus 1 to the 2n minus 2 over an n factorial. Okay, so that's what we're going to need, is that nth term from B, okay? So, cool. So now, the ratio test, right? The ratio test says that we do the limit, right? So the ratio test in part C, we do the limit as n approaches infinity of a sub n plus 1 over a sub n inside an absolute value. So that's going to mean that the top term is going to be this nth term with an n plus 1 plugged in for all the n's. So I'm going to get that this is the limit as n approaches infinity of x minus 1 to the, this is going to end up being 2 times the quantity n plus 1 minus a 2, right, over an n plus 1 factorial, right, all divided by the nth term already, which was an x minus 1 to the 2n minus 2 over an n factorial, right? So when I flip stuff over to clean it up, right, which we can probably get away with doing here because it's a slightly shorter ratio test problem than normal. So I'm going to go ahead and flip this up so the n factorial is on top of the n plus 1 factorial, right? And I'm going to get that this is an x minus 1 to the 2n plus 2 minus 2, which we'll deal with in a sec, over an x minus 1 to the 2n minus 2, right? And, oh, that's interesting. Okay, so really quickly, what you're going to notice, or maybe you don't notice really quickly, and that's okay, right, is that I end up getting, so the way factorials work is an n plus 1 factorial is all of the terms of an n factorial, right, like all of the numbers in an n factorial, right, n times n minus 1 all the way down to 1, but also an n plus 1. So when these cancel, I end up getting a 1 because all of the top numbers cancel over the n plus 1 that didn't cancel. And then here, I'm going to end up getting, so this is essentially going to end up being this is an x to the 2n, right? And this is an x to the 2n minus 2. When I subtract, I end up getting an x minus 1 quantity squared. But what's interesting is it doesn't matter. And the reason it doesn't matter is because the limit as n goes to infinity of a 1 over an n plus 1 is 0. So I end up getting 0. Doesn't matter what x is, which is less than 1. So the interval of convergence is negative infinity to infinity, because this is always true. There's no need for an x to make this be true. It turns out that when I do this ratio test, I get 0 is less than 1, which is true no matter what x I pick. 0 is always less than 1. So my answer is negative infinity to infinity. There's no need to test the endpoints because, again, converges for literally everything. Part D. Use the Taylor series for f about x is 1 to determine whether the graph of f has any points of inflection. Fun. Okay. So we have to, before we dive into this, right, we need to think, what does it mean to be a point of inflection, right? So in D, right, the ask was, does f of x have a point of inflection? They didn't ask you to find it. They just asked you to determine if it has any, right? Whether the graph has any, right? That's all they ask. They don't want you to find it. So very often, what they're asking essentially, so really what they're asking here is, does f double prime of x change sign, right? That's what they're asking, because that's what it means to be a point of inflection. So we need to use the Taylor series they gave us to see if we can figure out whether f double prime changes sign. And if I can show that all of f double prime is negative all the time, then I don't have to worry about a change in sign, and f double prime is always negative, and the answer is no. Or if f double prime is always positive, then I can say, oh, f double prime is always positive, and the answer is no. So let's walk through and see what we get. Okay, so we have this f Taylor series, right? So f prime of x is going to be the 2 is going to drop down in front, and I'm going to get an x minus 1 to the first, right? Plus a 2/3 x minus 1 to the third, right? Plus dot, 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 dot. If we work our way down, I'm going to get a 2n minus 2 x minus 1 to the 2n minus 3 over this n factorial, right? Cool. Dot, 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 dot. If I derive again, right, I'm going to get that this term is just a 1, right? When I derive this guy, I get a 2 times x minus 1 quantity squared. And when I derive this guy, I get a 2n minus 2 times a 2n minus 3 times this x minus 1 to the 2n minus 4 all over an n factorial. Okay, cool. All right, so dot, 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 dot. Okay, so here's the deal. 1 is a positive number, right? Because this has a positive leading coefficient and a squared term, which means this must also be a positive number, right? We know that the 2n minus 2 and the 2n minus 3 are always going to be positive numbers, because in a Taylor polynomial, you can't have negative exponents. So these are also positive numbers divided by n factorial, which is a positive number. And 2n minus 4 is also an even power, right? So even powers come out positive. So it turns out that this whole thing, every single term is going to net positive, right? And you can see that, again, by looking at this nth term. We know that the powers can't be negative because it's a polynomial. We know n factorial is not negative, and 2n minus 4 is an even number, because 2n is even, and subtracting an even number from an even number is even. So this whole thing comes out either positive or 0. So it would come out 0 at 1, but it would come out positive everywhere else. So it looks like f double prime of x is greater than 0 for x not equal to 1, and f double prime of 1 is 0. That means that f double prime never changes sign. So f double prime does not change sign. So there are no points of inflection, right? That's really what they want us to say. So essentially, because this whole series is non-negative, right? It's either positive or 0, non-negative. There's no change in sign, thus no point of inflection.